is more symmetry. So that's what the first part of this unit a lot is about, is our symmetry and our transformations again. So we're going to go over symmetry and then tessellations. So you should hopefully recognize that. Yeah. All right. A figure has, oops. All right. A figure has symmetry if there is a transformation of the figure such that the image coincides with the pre-image. Okay, do you guys remember our different transformations from last unit? Rotations, translations, all that stuff? And what was it called whenever a figure was mapped onto itself identically? What was that word we used? Dilation. No. Whenever they were the exact same, they were congruent figures. No, starts with an I. Isometry. There you go. All right. So we're going to be looking at a lot of isometries today. Line of symmetry. So a figure has line symmetry or reflection symmetry. Reflection. If it can be reflected across a line so that the image coincides with the pre-image. The line of symmetry, or we also call it the axis of symmetry, divides the figure into two congruent halves. Okay? So a lot of the times this line of symmetry, just in case you see it, is abbreviated by LOS, line of symmetry. All right, so tell whether the figure has line symmetry. If so, draw all the lines of symmetry. So does this Pac-Man have lines of symmetry? Can we draw a line somewhere folded on top of each other and it be the same? Yes. How many lines? One. And where would it need to go? Like through the mouth, right? So we got to draw it. And then we got to state how many it has. So we would say this has one line of symmetry. So I'm going to say 1 LOS. All right, what about the kind of big plus sign hospital looking symbol?
3.
3? Where do you see 1 at?
4.
4. Tell me where. Where to draw?
Okay, through the middle, like the top.
Okay, so we can draw vertical. All right, good. Horizontally. And you could draw diagonally both sides, correct? So that would be 4 lines of symmetry. All right, what about the right triangle? Does that thing have any lines of symmetry? No. So this is no lines of symmetry. What's that last figure called?
Octagon.
Octagon, good. So how many lines of symmetry do you think it's going to have?
8.
8. Very good. So let's draw them. Where do you think they are?
In the middle of each of them.
Good. In the middle. So there's 4. Where are my other 4? At the corner to corner, right? So this one has 8 lines of symmetry. Any questions? All right. So next, a regular polygon is equal angular, so it has equal angles, and equal lateral, so it has equal sides. Regular polygons have lines of symmetry equal to the number of sides or angles that they possess. So some of your regular polygons are below. An equilateral triangle, 3 lines of symmetry. A square, that's a regular quadrilateral. It's got 4 lines. A regular pentagon, 5 lines. A regular hexagon, 6 lines. And it keeps going. Any questions there? All right, flip it over. Rotational symmetry. A figure has rotational symmetry or radial symmetry if it can be rotated by an angle greater than 0 degrees and less than 360 degrees, so that the image coincides with the pre-image. Right? An angle of rotational symmetry is the smallest angle through which a figure can be rotated to coincide with itself. So how many times can you rotate it and it look identically the same? Okay. The number of times that that figure can coincide with itself, so the number of times it looks identical to itself, is called the order of the rotational symmetry. All right. So we got some different figures here. It says, tell if each figure has rotational symmetry. If so, give the angle of rotation of symmetry and use, and the order of symmetry. So this green X, does it have rotation? Can it rotate less than 360 and it look identical?
Yes.
Yeah. How many times does it rotate?
4.
Rotates and looks the same 4 times, right? So that means order is 4. So then if we know it can look identical 4 times, and there's 360 degrees in the full rotation, what's its angle of rotation? 90. There you go. So we would do 360 divided by that order equals 90 degrees of rotation. Any questions there?
Wait, isn't the maximum you can do this for?
Mm-mm. You'll see. All right, what about this triangle? When will it look the same? 360 degrees, right? It is not going to look identical to itself till it's all the way back around, correct? Okay, so then it would be no rotational symmetry. Oops, that would be able to spell. Okay, what about this little squiggle flag looking thing? What do you think? 2, order of 2. Okay, so its order is 2. So then how many degrees of rotational symmetry does it have?
180.
180, good. So 180 degrees of rotational symmetry. And the yield sign, school crossing sign, whatever you want to call it, goes for a lot of things. 3, good. Its order is 3. So then how many degrees of rotational symmetry does it have?
120.
120, good. Any questions there? Okay. Next, describe the symmetry of each icon. If there's line symmetry, draw the lines of symmetry. If there's rotational symmetry, give the angle and the order. So this yin yang, what do you think? Let's do line symmetry first. Does that have line symmetry?
Yeah.
Where would it have line symmetry? Mm-mm. Does not have line symmetry. What about rotational symmetry? No, why not?
Because it's different colors.
Right, the colors won't allow you to rotate and it looks the same until it's all the way back to the beginning. Does that make sense? Okay, so we have to state that it's got no line or rotational symmetry. All right, what about the box with the box inside of it? What do you think? Got line symmetry, good. How many lines does it have? 4, and it told us if there is line symmetry, we have to draw. So where are 4 lines? Diagonal. Diagonal both sides. Okay. Horizontal and vertical. Good. So we had 4 lines of symmetry. Now we need to talk rotational. Does that, yeah.
Do they have to be dashes or can it be lines?
You can draw straight lines. What about rotational? Does it have rotational symmetry? Yes. What's its order? 4. And so how many degrees of rotation does it have? 90. All right, any questions there?
Max was 360. So can it go over that though?
All right, next page. Same question, 2 different pictures. I'm going to give you a second to try and figure out line symmetry, rotational symmetry, draw the lines if it has it, state the angle and the order if it has it. Go. All right, what'd you guys say for the star? You said what? 3 what? Ooh,
5.
I agree with Aiden. 5. Where are your 5, Aiden? Good. Through each point of the star. All right, so 3 lines of symmetry. 5 lines of symmetry. Thank you. All right, what about rotational? What'd you guys say? 5 order, and so that's how many degrees? 72 degrees. Good. So your order is 5, so 72 degrees for the rotation. Any questions there? All right, what about this little green weird cell looking thing? 7 lines? 1, 2, 3, 4, 5, 6, 7. Yep. So 1 through every spoke. Did I get them all? Nope, I missed one. No, I got them all. So 7 lines of symmetry. So how many degrees does that mean? 51 point, I got 51.4. Okay, and what was its order? All right, any questions there?
Don't they always give you the same, the lines of symmetry?
Really? Okay, now.
I think so. Okay, any other questions? All right, next. Okay, we got this guy. So it says use this figure, and before we even start any of these rotations and things, what do you think we should figure out? So we're trying to rotate from one spot to another using different degrees, so what do you think? Because you've actually done something similar to this. Should probably figure out the angle of rotation. Okay, so 360 degrees divided by what's your angle of rotation? How often does it look like itself? 8? Okay. So 360 divided by 8 is how much? 45?
Yeah.
Okay, so that means each turn is 45 degrees. Does that make sense? Each turn is going to be 45 degrees for it to look like itself. Okay? All right, now we can figure out the questions. Name the image of DR rotated 90 degrees counterclockwise about point P. So how many turns is 90 degrees? 2 turns, right? So 90 divided by 45 degrees equals 2 turns. So if we start at DR and we want to go counterclockwise, which are we going? Which way are we going? This way, to the left. So DR, 1, 2, ends up where? IG. Here we go. Okay. Yeah. Any questions there? Okay, BI needs to be rotated 180 degrees clockwise. 180 degrees would just be opposite. So BI, what's the opposite of that? RE.
You can also say ER.
Yeah. Okay, what about AE? We need to rotate 270. So how many turns is 270? 6 turns. 270 divided by 45. 6 turns. So we're going counterclockwise. So AE, we're starting here, going to the left. 1, 2, 3, 4, 5, 6. Where do we end up? BM. Any questions there? All right, reflections.
Would
Yes.
you say clockwise?
Counterclockwise? Counterclockwise. All right. Name the image of RE if it's reflected over MD. So if we make a line of reflection at ME and we want to put RE on the other side, where's it at? GI. Very good.
Why is it not ID?
Yeah.
Because we're reflecting. So if we take this, we fold it in half, this segment right here is not going to end up over here because we're not going 180. We're reflecting over this line. So it's like 2 segments away from the line, so it needs to be 2 segments away from the line over here. Okay? Alright, now it says, where's the pre-image of IG if we reflect over GA? So we're reflecting over, oh goodness. So GA, and we want to reflect IG. Where would that end up? DG. Okay. Once again, a reflection is like folding it and seeing where it coincides. Where does it line up? So if we reflect over the purple, IG is one segment right here next to the purple. So if we reflect it, it's going to be the other segment on the other side of the line. Okay? All right. Next, tessellations. Do you guys remember what a tessellation is? Heard of it?
No,
Never heard of it? You guys didn't do, like, I remember back in middle school we did, like, tessellation projects in math and art. No? Well, middle school sucks now, apparently. All right, so a tessellation, or tessellations are patterns of repeating polygons or other planar shapes, so on the same plane, in the same plane, that completely cover a plane. So we repeat the same pattern over and over and over again. So the first one, we've got a beehive on the left, we got a pattern on the right. Stop and jot, so take a minute to yourself. How are these images the same as and different from the shapes we looked at in the first half of notes? So take a second, write down how they're similar and how they're different. Go. All right, what did you guys say? Someone give me an example of something they put. Yes.
They're continuous instead of just one big.
Okay, so we've got continuous shapes instead of just one we did in the last set of notes. Good. So that would be a good difference. We can write that down. Okay, that's a difference. Do we have any similarities? Do you see any similarities of these patterns? They're polygons. Yeah, they're what type of polygons? Regular ones. Regular what? What kind of polygon is it? Hexagon, thank you. They're regular hexagons. So, what was the whole first section about? Symmetry. Does it by chance have any? Is there any similarity there?
They're both rotational and line.
Yeah, you've got rotational and line symmetry still.
That was per argument.
Alright, so if a regular hexagon in the first half of notes had line and rotational symmetry, don't you think a continuous pattern is also going to have line and rotational symmetry? Yes, probably. Okie dokie. So if a pattern continues indefinitely, so if we continue this pattern forever, then it will appear unchanged when it is shifted up, down, left, or right. So this kind of symmetry is called what? What did we call that whenever we shifted up, down, left, or right and it looked the same? Translation. A translation shifted you any which direction and it created the same pattern. When a figure exhibits translation symmetry, there is a single shape that is the basis for the repeating pattern. So you guys identified that single shape up there in the pictures as which one? A regular hexagon, correct? Okay, so on the next page, we're going to identify these shapes. So it says work with a partner to identify the shape or groups of shapes that was translated to form each repeated pattern. So what shape or what group of shapes forms this pattern? So what single shape or group of shapes form the whole pattern? Okay. What shape or group of shapes forms this pattern? What shape or group of shapes form each of these? So try for a minute and talk to somebody next to you. What shape or group of shapes do you think helps form each pattern? Go. Okay, let's see how you did. So this first one here, if you remembered, you cannot rotate, reflect, you can only translate. Okay, so you needed to take two equilateral triangles. So your pattern could have been this repeated, two equilateral triangles on top of each other like a diamond. That was your base pattern. Over and over and over again, you could slide that. Or you could have done it kind of like this way, where you have one like this. So this could have been more like a parallelogram, and you could slide that one any which way you want. Okay, so you could have taken the diamond or the parallelogram. Any questions on that one? That's your base figure there. Okay, this next one was like a bird looking thing. That is an irregular polygon. So this was, I called it like a bird looking thing. So this is your pattern. That guy. Okay. And then the next one, you needed a square and yeah, it's like a square with corners plus this little diamond guy. 1, 2, 3, 4, 5, 6, 7, 8. Octagon. So a square and octagon. So you needed this guy. There. You needed that guy. So the little square and then the octagon. Use your basis for all of them. And then lastly, this guy, there were, it was a 2 equilateral triangles. And a hexagon, regular hexagon. There was 2 different ways you could do this one. You could have done like a big diamond like this. So you could have repeated that shape, so a hexagon with your triangle on top and triangle on bottom. Or you could have repeated the hexagon with kind of like an hourglass shape next to it. So it looks like an arrow almost. So those are your 2 possible shapes inside there that got repeated over and over and over again. So like a diamond or like a arrow, a big arrow. Any questions about symmetry and tessellations? Okie dokie.